right. So because entropy of gases is going to depend on their pressure, their volume, their expansion, that type of thing, we can kind of work that into free energy and spontaneity, because remember, if the entropy in the universe increases, a reaction is spontaneous. So if you look at this equation, we have delta G twice. What's the difference between them? One has a little degree sign, which means it's the standard, 25 Celsius and ATM. So that's your standard delta G. This R is going to be 8.31. We want to use the one that's got joules in it. And then temperature still in Kelvin, and we've got that related to reaction quotient. Remember, that's the fake equilibrium constant. It's when you take the equilibrium constant expression with the products or the reactants, but you do whatever's given. And that's going to give you a free energy change under those given conditions. So it's not necessarily standard conditions, because standard conditions is 1 ATM. It's whatever pressure conditions you're given. And then by your G being positive or negative, you can tell, like if it's negative, that means the reaction is spontaneous going forward. So the reaction is going to go forward from left to right to get to equilibrium. But if delta G ends up being positive, that means it's not spontaneous going forward. So where is it spontaneous? Going backward. So the reaction goes backward to get to equilibrium. And that's all for that. And like I said, we'll do it as sample at the end. If we change that Q to an equilibrium constant, and then this G would be 0. So you have to remember, when we do these calculations, it's before the reaction has happened. So we're saying we're going to put these gases in a container at these given pressures. We calculate the delta G, and then let the reaction go. It's going to come to a point where all the free energy has been given off or taken in to make it go, and delta G goes to 0. So if we set delta G to 0 and Q to K, we get this next equation, which is a lot more usable. And then we'll do the examples, and I'll kind of make a little more sense. You have to remember that equilibrium constant is products over reactants, and delta G is products minus reactants. So that's what sort of like the relationships mean. But every system is going to go where it's the most stable. Everything's going towards its lowest energy point or its stability point, which a lot of times is equilibrium, not total products. So that's why we can have a relationship between spontaneity and equilibrium by using this equation, delta G equals negative RT ln K. And again, we're talking about T in Kelvin and that same R from the other slide, the 8.31. This is what's important down here, we know that when delta G is less than 0, the reaction is spontaneous going forward. And if you think about delta G being products minus reactants, that means the free energy of the products has to be less than the free energy of the reactants, because that would give us a negative when we subtract them. But that also means that K is going to be greater than 1, because K greater than 1 means if K is products over reactants, it means we get more products. So all of those things are related. A large K means going towards the products. A negative delta G means going towards the products. So the reaction goes to the right until it gets to that equilibrium system. And then if delta G is greater than 0, we have the opposite. The reaction is not spontaneous going forward. It's actually spontaneous going reverse. K is less than 1. It favors the reactants. So the equilibrium is going to lie on the left. There's going to be more reactants than products at equilibrium. The reaction is going to go in reverse instead of going forward. But again, you have to remember that when you calculate delta G, you're doing it as if you haven't put the stuff together yet. And eventually, it'll take in its energy or lose its energy and go to a point where it's at equilibrium, and there's really no more energy to be had. Equilibrium is essentially like the end point of the reaction. So we're going to try one example. So again, because we're very equation heavy, it's kind of looking at what you're given and decide, like, what equation do I have that's going to match what I want to do. So we're given a reaction, and we're given the standard G, H, and S. Make sure you take notes of the units for when you need that information. A says estimate the value of the equilibrium constant. Well, what's the only equation we have so far that has the equilibrium constant in it? The one we just did, right? The only one we have with equilibrium constant in it is delta G equals negative RT ln K. So let's do it. Now, delta G, I've got negative 198 kilojoules. What's the unit of R? Joules. So I do need to put this all into joules. So I'm going to do negative 198,000 joules equals negative 8.31. Temperature, 298. ln K. Do y'all know how to solve that? Do negative 198,000 divided by negative 8.31 and divided by 298. Get ln K to be 79.96. How do you find K?
Power time.
You need the E. So like just like we were doing in last unit, second log, do second ln. And when you do second ln, it says e to the. And depending on how you round K, you will get like very different answers. Like just putting the whole answer in, I get 5.3 times 10 to the 34th. But like if you had rounded it to 79.9 or 80, you get a very different answer. You get like 5 times 10 to the 34th. So when you start checking these in the back of the book, look more for the power of 10, because rounding your K can make a big difference. That was easy. All right, for part B, it says estimate the equilibrium constant at 700 Kelvin. So your first instinct is going to be to do what? The same thing with 700, but there's a catch. Because that G is measured at what? At STP, it's at 298, it's not at 700. So what we have to do first, and this is why the delta G equals negative RT ln K always has the degree, is we are going to find delta G, an approximation at 700, and then do this equation by doing first delta G equals delta H minus T delta S. We're going to do this at 700 Kelvin to estimate delta G. Now, why am I only going to get an estimation doing this? Here's my delta H. I'm going to put it all in joules because it's easier later. So I'm putting in 700 for delta T, for T. Oh, I should put this whole guy into brackets so we don't like, make sure you subtract the whole thing. And I'm going to get negative 195,500 joules. It is better to round at the end if you can. Why is that only an approximation at 700 Kelvin? Because H and S are still at 298, and we don't have charts for H and S at all these different temperatures or a way to adjust them. So anytime you use H and S at a different temperature to try to calculate a new delta G, you're really just getting an approximation. So that's giving us an approximate delta G at the new temperature. And now I can take that new delta G and do the negative RT ln K with my new temperature. So I'm actually using two equations. I'm doing delta G equals delta H minus T delta S, and then I'm doing delta G equals negative RT ln K. So if you do change from that standard temperature, it's not just about changing the temperature in the negative RT ln K. You actually have to go back and do a new approximation for delta G. That's kind of the only twist. Do y'all have any questions to there? So just watch the temperature, watch the units, Make sure when you're using the negative RTL and K, G is in joules, because R is in joules. All right, if you look at C, we got a bunch of crazy stuff going on that we didn't even talk about. But we kind of did. If you're given all these different pressures, we want to use the one with Q. Those pressures are going to help us find Q. We don't know if we're at equilibrium. We don't know where we are. So let's do Q first. Q is doing products over reactants, right? So I've got NO2 at 1 times 10 to the negative 7th. These are all ATMs. I'm being a little lazy about the units. 1 times 10 to the negative 6. And 2 times 10 to the negative 6. Wow, I'm lazy about the sig figs also. All right. This all works out to a Q of 50. And we're back at 298, so I don't have to do anything special to delta G. But once you guys have this written down, I'm going to get myself a new page because I don't have any room down here to finish. All right, so we're going to use now this delta G equals standard delta G plus RT ln Q, and we're going to plug everything in because now we know what Q is. So we're going to do delta G equals, remember the standard delta G is on the other side of the equals. I got to keep it in joules. 8.31, I'm at 298, and I just found Q to be 50. So I get negative 188,000 joules. So when this reaction, which is not at equilibrium, goes to equilibrium, which way is it going to go? Does it go to the right to get to equilibrium, or is it going to go to the left? Which way is it spontaneous? Forward is spontaneous because we got a negative sign there. Negative sign means forward is spontaneous. So we can tell that this reaction has to go to the right. It will release free energy to get to equilibrium. It's kind of like that whole, if we knew K, the Q is less than K, it goes to the right. If Q is greater than K, it goes to the left, that type of thing. So when you get to your homework and you get a problem that's got a bunch of little pressure values in it, you know that you're finding Q. And if it asks you which way the reaction goes, all you have to do is look at the sign of G, or you can find K and compare Q to K, just like we did last unit.